We're asked to find the pH, and we're given the initial concentration of a weak acid, hypochlorous acid, and we're given the Ka, the acid dissociation constant. We've been writing this generically, but let's write this dissociation between hypochlorous acid, and that's going to dissociate into the H+ ion and the hypochlorite polyatomic anion. You could have written this generically as, so we'll do both ways. And there's a conjugate base. That might be too much on the screen. All right, so we're going to set up a nice table where I stands for the initial concentration, C stands for the change in concentration, and E stands for the concentration at equilibrium, and this is what we need. So we can use this equilibrium constant. We're given the initial concentration of the weak acid is 0.275 moles per liter, and we assume there's none of the products. And we're going to say the change is some quantity X, and because these are all 1:1:1 mole ratios, the change in one of the products is going to be the concentration of the change in the other. And that's also going to be the same amount the reactant decreases by, because the reactants are used to make the products. To find the concentration at equilibrium, we're going to take the initial, add the change to get the concentration at equilibrium. So it's going to be 0.275 minus X for the weak acid, and for the hydronium ion concentration and the conjugate base concentration is going to be X. So now we can plug this into the equilibrium expression. Let's see what was the constant. 3 times 10 to the negative 8. So Ka is given to us 3.0 times 10 to the negative 8. That's going to equal the concentrations of the products over the concentration of the weak acid, the hypochlorous acid. We found that out to be, we're going to plug that in there, I'm going to plug that in there, and I'm going to plug that in there. X times X on the numerator is going to be X squared, and on the denominator it's going to be the 0.275 minus X. This is going to be negligible compared to that. So when you're subtracting a number that's much, much smaller, that's doesn't even have sig figs to account for it, then we can ignore that X. Now we can't do that on the numerator because that's all we have, and you're taking a square, which is a much, much bigger, going to make a bigger difference than just adding or subtracting a number that's orders of magnitude smaller than another one. Cross multiply here, and we're going to get X squared is equal to 3.0 times 10 to the negative 8. Multiply that by the initial concentration. Take the square root of both sides to get X. So if you've done enough of these, you can skip right to the step where you know X is going to equal the square root of the Ka value times the initial concentration of that weak acid. That's it. Square root of that, and you get your answer. Shortcut. All right, so let's plug these numbers in. All right, now X is not our answer. It's 9.08295 and so on times 10 to the negative 5. That's not our answer. That is the concentration of hydronium or hydrogen ions. The question I'm sure is asking for us for pH. Find the pH. Yep, so we've got to take the negative log of this. So take the negative log of that number, which is still stored in my calculator. Negative log of the answer. And that's going to give us a pH of 4.04. How many sig figs do we need? So we're going to use the 2 digits here, and our answer is going to have 2 digits to the right of the decimal. So 4.04 is our answer. Now, some of you are like, why did we ignore that X earlier over here? Like, why did we ignore it right there? Because it wouldn't have made a difference. I used a quadratic equation. Well, I didn't, but I plugged in the numbers in the website, and just to show you we get the same answer. Take the negative log of that. That's what hydrogen ion concentration is. Guess what you get? You get pH is equal to 4.04. It's exactly the same answer. Oh, now wait a minute. There's also one other thing you might be asking is, I'm not going to have time to do this, but in another video I'll do it. You might be wondering, what about the concentration of H plus due to the water, which is 10 to the negative 7, right? Well, that's in there too. All right, so you gotta ask yourself, 10 to the negative 7 is you're right, that is contributed by pure water that this is in solution of. It's a solvent. But is 10 to the 7 going to make a difference when the contribution from the acid is 10 to the negative 5? No, it's not. It's orders of magnitudes smaller.